Hello EmacsConf, my name is Troy Hinckley, and this is my talk on Rune, a Rust implementation in Emacs. We tried to be bug compatible with Emacs so you can use the same elisp. It's still a very early stage experimental project, and we have some basic things implemented. So before I get started, I want to talk a bit more about what the core is. So the Emacs core, it includes the runtime, the interpreter, garbage collector, everything used to run the code. It includes the GUI. It includes all the data structures. If you look underneath all the elisp data structures, there's C code underneath there, as well as the auxiliary functions, of which there's about 1,500. And in making this talk, I don't want to give the impression that I'm saying the core is outdated or that it needs to be replaced or that it can't be evolved on its own, because clearly it has continued to evolve. If we look in just the last few years, we can see that we've added native compilation, we've added tree sitter support, we've added color emoji, and there's work right now to add a new garbage collector to Emacs as well. So why create this project? Emacs has a long history, it has a lot of users, it needs to support a big community. And so because of that, it has to be very conservative about what things it can allow into the project. And forks like this create an opportunity to experiment and try new approaches. And this is particularly a good use case for Rust because the C core, it's pretty well tested. It's been around for a long time, a lot of the bugs have been ironed out. But when you're doing a new greenfield project, it's very easy to introduce new undefined behavior and memory unsafety and stuff like that. And Rust protects us from most of that, but it also gives us the ability to be fast and has a strong ecosystem behind it. Rust is also really good at multi-threading. Their phrase in the community is fearless concurrency. They should be able to write concurrent programs without having to worry about data races. It's also really high performance. It has a really good Regex engine. It's known for its non-copy I/O as well. So how does this compare to other Rust and Emacs projects? Well, there's been a couple. The first is Remax. So this project was the first. It took an outside-in approach. So basically, you could take a C function and replace it with a Rust function and build it together as one executable. And this is pretty easy to do because they could both talk over the C ABI, and you could swap out functions once at a time. So they made really good progress at first. But eventually they ran into the problem that as you get down to the really core parts of it, you can't just replace one function at a time anymore because some of that functionality is connected to other things. Like for example, you can't replace the garbage collector without replacing the entire garbage collection system. And so the progress really kind of slowed down. Another issue with it is that they were doing a one-to-one rewrite. So they weren't adding any new features or functionality, just taking the same code and replacing it in Rust, which doesn't add any advantages in and of itself. So this spawned Emacs NG, which was kind of the spiritual successor to Remax, where they decided to add new functionality, the biggest one being a JavaScript runtime, as well as some new renderers to Emacs. This is no longer actively developed though. So in this project, one of the big focuses we have is on multi-threading. The C core itself everything is designed around being single-threaded, all the data structures and everything like that. And Rust has a great concurrency story. In Rust, everything is intended to be multi-threaded. That doesn't mean that everything has to run on multiple threads, but you can't write something that is limited to only running in a single-threaded environment. And so this makes it really easy to use all the existing packages and build something that is concurrency safe, which is what we've done here. And that was relatively easy to do. But adding it to elisp is the hard part because we got to come up with a good model for the Lisp, and elisp is just a giant ball of mutable state. So we need to find some way to tame that so we can make workable concurrency out of it. And there's really two ways you can do this. One is what I call the No-GIL method. This is what Python is doing, where you take all of your data structures, you make them concurrency safe, and then you just leave it up to the programmer to decide what they're going to do with it. They've got to build safe abstractions on top of that. One of the big downsides with this is that it comes with a pretty high cost. The last benchmarks I've seen is that by making everything concurrency safe in Python, single-threaded code is about 20% slower in some benchmarks. And so since most code is single-threaded, this has a big performance impact for most code that isn't taking advantage of the multi-threading. The other thing is this introduces a lot of nasty concurrency bugs because you can have anything mutating any part of the data from any thread, even if you can't have memory unsafety per se. The other option is actors, which are a really known way to approach this, where you trade some of that flexibility that you get with fully concurrent for more control. And code and functions are shared between all the different threads, but data has to be passed along channels between different actors. So we want the functions to be shared, and this should be pretty easy because we don't mutate functions like we do data, except when we do. So in Lisp, Functions are just lists like anything else, and so you can mutate them just like lists. And even if you're not talking about interpreted code, like even if you have a native compiled function, you can still mutate the constants inside the function. For example, here we have a function returns a string. We take that string out, we mutate that string, and now the function returns a different string. So in Rune, we enforce that all functions, their constants are immutable. You can't mutate the insides of a function. You can still swap out functions and redefine them, but you can't mutate the inside of a function. So this enables them to be safely shared across threads. However, there are some caveats to this. For example, some functions actually do need to mutate their own data. The example that we run into is CL generic. It uses a method cache, and so it has to be able to update that cache. And in this case, we just made a special case for this particular situation, but we don't know what more of these we're going to run into in the future, where this is needed behavior to be able to mutate a function. Okay, so functions are pretty easy. They just can be shared between threads, but data can't be immutable. At least not inside the model that Emacs currently has. So we have two different ways to handle this. One is we require, whenever you're calling some other code in a different thread, you have to send all the variables that it's going to need over to that thread. And this is how you traditionally do it inside actors. Any data that needs to go to a different actor needs to be sent over a channel. It's relatively easy implementation. But this is difficult in the Emacs case because everything is going to be accessing different variables, and that means when you call something, you have to know ahead of time all the different variables that are going to be accessed inside that other thread and put those in when you call it. So the other option we're using is we're copying values to the other threads on demand. So if you're running a thread, it tries to look up a variable, it doesn't have any value for that variable, it will go back and ask the main thread, and it will copy that value into that thread, and you can continue execution. This is nice because you can just launch some code and it'll take care of handling all the data transfer for you. What we don't want to be copying around is buffers because they can be really large. So in this case, we have a mutex. Each thread can only have one current buffer that it has an exclusive lock to. This comes with some trade-offs. Big one being that if the user tries to access some buffer, they want to type something, and a background thread is holding onto that buffer, what do we do in that situation? And we still need to hold an exclusive lock even if we're only going to read a buffer. If you have multiple readers, they each still need to take turns because we can't determine if at some point a thread is going to try and mutate the buffer. So it has to be an exclusive lock. The other issue is buffer locals. And this is less of a implementation issue as much as it is a technical issue. Because you think about when we switch to a buffer, it has some buffer local data and we have some thread local data. And as we go through, we're mutating everything, those can get intertwined and pointing to each other. And then when we switch away from that buffer, we need some quick way to be able to separate those out. So the buffer locals can go with the buffer locals and the thread data can stay with the thread data and make copies of anything that was pointing to the other side. But we don't have a good method to determine how to separate those two, like what data belongs to this and what data belongs to this, so that we can do that quickly. And we haven't found a good solution to that yet, but it's something we're still working on. So the question is, would this actually be useful for doing real work inside Emacs? And I would say, yes, there's a lot of things you could do with this. You could handle process output in the background. You can do syntax highlighting. You can do buffer search in parallel. You can do elisp. You can do fetching your mail in the background. You can have a window manager that doesn't block your window manager when Emacs is blocked. And as well as you could do something like a file system watcher that keeps up on files without blocking Emacs. This wouldn't be so great for building concurrent data structures or operating on shared data or building your own abstractions because the trade-offs that we've made here. Okay, so that's talking about multi-threading. The other thing we're going to talk about is precise garbage collection. In Rune, we have a safe, precise garbage collection because of the REST type system. So let's look at what the problem is with garbage collection in the first place. And really the tricky part about garbage collection is rooting. How do we find out what the roots are? And these are all the values that are on the stack or inside the registers. So in this example here, we allocate an object, we call garbage collect, that object's collected, and then we try and return it, it's no longer valid. So let's look at how Emacs used to deal with this problem, way back in the day. There was a system called GC Pro, or GC Protect, which is basically designed that every time a value needed to survive past a garbage collection point, you had to try and protect it. And in order to do this, you had to declare a struct, you had to put a macro around it to root the object, and then you had to unroot it when you were done, past the garbage collection. And now the value is safe. You can see down here, I pulled these 8 rules out from a really old version of the Emacs manual about all the things you had to keep track of when you were trying to use this system. All right, so there was a special handling for nested GC protects. You had to make sure the memory was initialized. You had to make sure that traps couldn't occur between allocating and when GC protect would happen. And it can be tricky because you don't always know when a function that's getting called could potentially call garbage collection. And so if you got something wrong, you also might not catch it for a long time because garbage collection may only get called 1 out of 99 times. The other 99 times is just fine. And that one time it happens and you can't reproduce the issue. And when you do get this wrong and something doesn't get rooted and it gets overwritten, it generally doesn't show up right where the problem is. It gets showed up way later when you actually try and access the value and the value is invalid. And you got to track it back to where that thing did not get properly rooted. So it's a huge source of bugs and very hard to maintain. So the Emacs decided to go with a different path, which we call conservative stack scanning. So basically the garbage collector just looks at the stack and all the registers, and any data inside there that looks like it could be a pointer, it treats it as a pointer. This is nice because you get really easy root tracking, but it also comes with some trade-offs. Mostly that your objects are no longer movable. So why would we want movable objects in Emacs? There's a couple different reasons. One is compaction. You can take all your heap, you can pack that on down because you can coalesce all your objects together. Another is that it's easy to implement generational garbage collection. You can just copy everything out of your minor heap into your older heap. And really, Emacs is kind of uniquely ideal for generational collection because the typical way we interact with Emacs is as a series of commands. You execute some command, you execute the next command, you execute command. It could be happening every key press. It could be happening with MX. And however long that command is, that is the ideal length for the minor collection generation, the first generation. Because once you're done with that generation, anything that's still existing is going to be around for a very long time. And so that works out really well for Emacs. So we want to make this a generational collector. The other thing is with object layout. We use a lot of lists inside Emacs Lisp. And every time you go to the CDR, you've got to be chasing a pointer around the heap and following that. And that can potentially result in cache misses and all sorts of other things like that. And so it can take a long time. It can be quite slow. But if you have the ability to move objects, you can just relocate an entire list and lay it out in an array right next to each other inside memory. And so iterating over it is just as fast as iterating over an array. But you can only do that if you have movable objects. And I'll point out here too that with conservative stack scanning, it's not that all objects are immovable. It's only ones that are pointed to from the stack or from the registers that have to become immovable. So let's look at how Rust makes precise garbage collection easy. So here I have some Rust code to show kind of how the lifetime system works and what we call XOR mutability, where we can only have one mutable reference or multiple immutable references to the same thing. So here we declare a vector, we take a reference to the first element of the vector, and then we mutate the vector. Now this could potentially resize the vector and move it to a different location in memory. And so that reference is no longer valid. And the nice thing is, Rust catches this for us. It says, hey, this is no longer valid. This reference can't survive past when you mutated it. Okay, that's exactly what we want for a garbage collector. You can see here, we take this in a garbage collection context. We create a new context object. We add an object. We call garbage collect. Then we try and access that object. It's no longer accessible. And Rust will prevent us from trying to access that variable. It's good. And so how do we solve this? We have a root macro. We declare this root macro. It lets us take that object and let it live past garbage collection. And everything works out. And the nice thing is, this root macro will get dropped when it's out of scope, so we don't have to worry about the un-GC protect step of this. So statically, Rust will verify and tell us any object that needs to be rooted. If we try and access it, it'll tell us it's invalid. We add this root macro, and then we can access it. And so in that way, we have safe, precise garbage collection without any chance of introducing undefined behavior, which is really, really powerful. And it's really easy because the type system will catch it all for us. There's some other Rust niceties I want to kind of talk through that are useful but are not, star features. One is proc macros. So you can see up on the top, you can see how you declare a function inside the C core. All right, you have to use the macro, you have to put the list type, the function type, the struct type, the different types of arguments or different number of arguments, the doc string, and then you can put your argument listing down inside there. On the Rust side, we just write this like we would any other Rust function. And then we put the defun proc macro on there and it takes care of everything for us behind the scenes. And a couple cool additional things we can do with this is that we don't have to make everything just an object. We can actually make things more specific types. So here we have symbols. And as well as you can see subfeature, it's an optional parameter, and we just make it an option inside Rust, and it automatically make it an optional inside elisp. This makes them really easy to write. And I can't take credit for this because this is something that I saw inside Emacs and I stole from them, but it makes the functions really easy to call from each other and really easy to write as well. Another thing that's really nice is sum types. So in the C core, if I wanted to get a string out of an object, I would first need to check that it's a string and then dereference it as a string. But if it's not a string, I'm going to introduce undefined behavior. And so in complicated code, I have to make sure that I have always checked what type it is before I try and dereference it to that type. We don't have to worry about any of that inside Rust because we can untag a value and we can use their sum types, basically create an enum, and we can match on what the different values can be. And then we only get out the types that are viable or are actually there. And so we never accidentally get something out of an object that we didn't mean to, or dereference it something that doesn't really exist. We can just match on it and we can get out the values that we need, which is really, really powerful. So there's some other Rust niceties as well working with here. One is the Regex engine inside Rust is really fast, high performance. And we are using that for the elisp Regex engine to give it high performance and worst case guarantees. The other is that Rust has a lot of really good parsers for things like JSON that are no copy parsers that are high performance, and we can use those inside Rune as well. There's a handful of other changes we're working on that are not Rust specific, but we'd like to see. The first is being GUI first, terminal second. So this means two things. First is that we have all of our key bindings. Right now inside Emacs, Control-I and Tab are bound to the same key binding by default because that's how it works inside the terminal. In the GUI, you shouldn't have that limitation. The second is that the GUI should not block when Lisp is blocked. It should be independent of that. So your GUI can still continue to operate when Lisp is running. The other is the ability to have an off-screen cursor so that you can be typing on something, you can scroll up and down, and the point doesn't have to follow you where you lose your place where you were before. You don't have to intentionally set a mark. You can just scroll and then start typing and it'll go back up to where it was before, like it works in most applications. And this can be optional. The other is image flow. We want it so that you can easily flow images and you can have large images and scroll past them without jumping, and you can flow text around images. How are we testing this project? Because there's a lot of things that you could get wrong here. One thing we're doing is we're using ERT. So Emacs ships with over 7,000 built-in tests, elisp tests. And we are using this test suite to test our project as well. So we can kind of use this as a dashboard of saying how close are we to getting to parity with GNU Emacs. The other thing that we have is a tool called lprop, which is an external utility that basically tests for correctness. Because really, the correctness of Rune is whatever Emacs does, because there's no official spec on how things should behave. And so to do this, we can go look at the Rust function signature. And we know what the arguments are, we know how many they are, and we know what types they should be. And given that information, we can generate a whole bunch of random functions feeding those types in. And then we send a copy over to Emacs, we send a copy over to Rune. They each evaluate it and they return the result. And we make sure the results are the same. And then we do that for thousands of different implementations of the function. And it helps us find corner cases really easy without having to handwrite a whole bunch of different cases to test things and say, where are these two functions different? So the current status, we already have a multi-threaded elisp interpreter and bytecode engine inside there. There's no actual text editor in there yet, but the primitives are there. Like you can insert text, move point around, delete text, do different things like that. But we don't have a GUI hooked up to different key bindings to actually type on. There's just a REPL to operate in. We have about 250 of the 1,500 built-in functions already implemented inside there. There's a lot of low-hanging fruit inside this area to still be implemented. The next directions we're working on is we're optimizing the GC. We want to make it generational. Like I said, right now it's just a simple semi-space copying GC. We want to add a proper GUI. We need to implement text properties, overlays, process and job control, all that goodness right there. So how can you get involved? This is hosted on GitHub. You can come on over. If you have any ideas about how to implement something or something you'd like to see done, go ahead and just open an issue so we can have a discussion about it. We've had lots of interesting discussions with different people coming in to the GitHub repo. If you're interested in contributing, the easiest way is probably to run lprop, pick some function, run lprop on it. I promise it won't take long to find some issue, some discrepancy between Emacs and Rune, and that lets you dive into the Rust code and figure out, and the C code, and figure out what the difference is between the two. Or come along and help implement your favorite functionality. This has been a really interesting project so far, and we've had a handful of different contributors on it who just kind of want to learn Rust or get more into systems level programming. Thank you.